Hello student, I am Dr.A.K, Professor of Chemistry. Today I am going to discuss the P block elements. Last class I have finished completely S block elements. Now I am going to discuss P block elements. In P block elements, the last electrons enter the outermost p orbital as we know that the number of p orbital is 3 and therefore the maximum number of electron that can be accommodated in a set of orbital is 6. Consequently, there are 6 groups of P block elements. 6 groups. Okay, there are 6 groups of P block elements in the periodic table, numbering from 13 to 18. 13, 14, 15, 16, 17, 18. Total 6 groups. Boron, carbon, nitrogen, oxygen, fluorine and helium head the group. Boron, carbon, nitrogen, oxygen, fluorine and helium head the groups. Their valence shell electronic configurations is ns2 np from 1 to 6 except for helium. The inner core of electronic configuration may however differ. The inner core of electronic configuration may however differ. The difference in inner core of elements greatly influence their physical properties such as atomic and ionic radii, ionization enthalpy, etc., as well as chemical properties. Consequently, a lot of variation in properties of elements in a group of P block is observed. Main region is D block and F block. Consequently, a lot of variation in properties of elements in a group of P block is observed. The maximum oxidation state shown by a P block element is equal to the total number of valence electrons, that is the sum of S and P electrons. Clearly, the number of possible oxidation state increases towards the right of the periodic table. In addition to this so-called group oxidation state, P block elements may show other oxidation states which normally but not necessarily differ from the total number of valence electrons by unit of 2. Again I am telling you that the sum of the S and P electron, that is the oxidation state. Okay, the number of possible oxidation states increases towards the right of the periodic table. In addition to this so-called group oxidation state, P block elements may show other oxidation states which normally but not necessarily differ from the total number of valence electron by unit of 2. That oxidation state may vary by 2, by unit of 2. The important oxidation states exhibited by P block elements that I will tell you that they will exist. They all have minor difference in oxidation state. Okay, I will tell you the important oxidation states exhibited by p block elements. I will tell you in these things in exhibited by p block elements. Okay, particularly in boron, I am talking of boron, carbon and nitrogen families. In boron families, carbon means 13, 14, 15. In boron family, carbon family and nitrogen families, the group oxidation state is the most stable state for the lighter elements in the group, that is in the beginning only. However, the oxidation state 2 unit less than the group oxidation state becomes progressively more stable for the heavier elements in each group. The occurrence of oxidation state 2 unit less than the group oxidation states are sometimes attributed to the inert pair effect. Means before P, s orbital will be there. They have 2 orbital. They have 2 electron. Before P, they will have s orbital. That they will and this s orbital will have 2 electron. Then generally these 2 electron will be strongly held by the nucleus, because screening effect will be not too much. That's why it will not will be in a position to lose that 2 electron. That's why it is called inert pair. Inert pair, because direct influence will be there of nucleus, because in the middle they will not screen fully, they will screen partially, hence it is difficult to remove these 2 electrons. That's why it is called inert pair. This I am telling you these things before going further. I am telling you general electronic configuration and oxidation state of p block elements. First 13 I will tell you. Actually there are 13, 14, 15, 17, 16, 17, 18. 6 groups are there under p block elements. Then 13 general electronic configuration I am talking about. 13, that is the boron group. It is ns2p1. ns2np1. n is the orbit number. And 14, now again 1 will increase. ns2np2. 15, again 1 will increase. ns2np3. 16, ns2p4. 17, ns2np5. And 18, ns2np6. Okay, this I have told you, 1 in increased, and ns2 is common. Then this I have told you electronic configuration, and this ns2 everywhere is there. That is very difficult. They will not lose the electron in easy way. Okay, that's why we are decreasing -2 unit in oxidation state. Now first member of the group of 13, group 13 is boron. Okay, and for 14 it is a carbon, and for 15 group it is a nitrogen, for 16 group it is oxygen, for 17 group it is fluorine, and 18 group that is the helium. Now oxidation state is just to see here for carbon, not for for boron 13. Boron 13, its oxidation state is +3. Okay, +3. And this is a small size. Boron is a small size. Then here maximum its group oxidation state is +3. And for 14, that is the for carbon it is a +4. Maximum is +4. And 15, that is the nitrogen, it is maximum is +5. And 16, that is a +6. 17 +7. And 18 +8. This is the maximum oxidation state. 1 increased. +3, +4, +5, +6, +7, +8. Now you can see other oxidation states. Then here I told you that last orbit, in the last orbit 1 electron is there in boron, NH2 NP1. Hence last electron will be that this boron can lose a last electron, only 1 electron. That's why its other oxidation state is +1. Now come to the carbon group. Here NS2 NP2 is there. NS2 NP2. NP2. Then here it can lose p electron, means 2 electron it will lose. That's why +2. And after that maximum is 4. Okay. And nitrogen NS2 NP3 is there. Then this they will lose 3 electron. Either they can lose or they can gain. Hence +3 -3. And in carbon also +2 they will lose, and -4 also. -4. Okay. Because they have to complete the octet. Octet means 8. Then in carbon 4 electrons are there. Then 4 electron they can take. That's why +2 is possible and -4 is also possible, because total 4 electrons are there. 2 + 2 4. Then to get octet 4 electron they require, and -4. And here in nitrogen already told you NS2 NP3. Then +3 is possible. Plus now total they have 5 electron. 3 + 2 5 electron. Hence 3 electron also they can take to complete the octet. Hence -3 is also possible. And 16, that is the oxygen. Here last orbit 4 electrons are there. NS2 NP4. 4 electrons. Then now +4 is possible. +2 is also possible. Okay. And because NS2 NP4 total 6 is there. For the octet 8 electrons are required and 6 are there. Then 2 electron also they can take. Hence -2 is also possible. And now fluorine NS2 NP5. Then +5 is possible. And after that total 5 + 2 7 are there. Then 1 -1 is also possible. And if you will see the electronic configuration, P has 3 type of P's are there. PX, PY, PZ. Hence +3 oxidation state is also possible. Then +5, +3, +1, +1, -1. All things are possible. Okay. Electronic configuration P5 is there. Keep in mind. Then 1 electron in P3. Now 1 electron it will go. Then 3. Again 4 and 5 they will paired up. Then 1 electron will be left, because P has maximum 6 capacity. Hence here that is the minus 1 is also possible, and plus 1 is also possible, and plus 3 minus 3. Hence 4 oxidation states, other oxidation states 4 are possible. Plus 5, plus 3, plus 1, minus 1, and 18, that is the helium. Then now here total plus 8 is there, because actually in the case of helium only 2 electrons are there, and maximum plus 2 they can give. Okay. Now here, but in other cases, other members of helium group, they have 8 electrons. Then they can lose plus 6. They have oxidation state plus 6, plus 4, plus 2. Okay. 3 oxidation state is possible in helium group. Okay, but only in helium plus 2 maximum. And other they have 8 electrons. Then why maximum possibility is plus 8. And if you will see the electronic configuration, then you will find that S square is also there, S square, NS square, and NP6 is there. Then P6 is there, then plus 6 is possible. And after that S square is there, then plus 2 is also possible. And if you will see the full electronic configuration, then you will find that plus 4 is also possible. This I have told about the oxidation states in details. The relative stability of these two oxidation state means group oxidation state and 2 unit less than group oxidation state may vary from group to group, and will be, and at the appropriate place I will discuss it. Okay. It is interesting to note that non-metals and metalloids exist only in the P block of the periodic table. Question is asked. Okay. Here we should note that the non-metals and metalloids have both metallic and non-metallic property. That is the characteristics of metalloids. Metalloids will be on the boundary. That's why boundary of metal and non-metal. That's why they will have character of both metal and non-metal, and is called metalloid. Then this I have told you about the these things, metalloid, and this non-metals and metalloid exist only in the P block of the periodic table. The non-metallic character of elements decreases down the group. As we will go down, then metallic character will be more, non-metallic character will be less. Then non-metallic character of elements decreases down the group. In fact, the heavier elements in each P block group is the most metallic in nature. In every group, in every 6 group in P block elements, down elements are, you can say, metal, or you can tell most metallic in nature. This change from non-metallic to metallic character brings diversity in the chemistry of these elements depending on the group to which they belong. In general, the non-metals have higher ionization enthalpies. In general, I am talking about non-metals have higher ionization enthalpies and higher electron negativities than the metals. This is the important things I told you. Hence, in contrast to metals, which readily form cation. Non-metals readily form anions because they are non-metal. They have electronegativity will be more. They want electron, and metal wants to give electron. Okay, then these non-metals will form anion, and metal will form cation. The compounds formed by highly reactive non-metals with highly reactive metals are generally ionic. Again, you listen important things. The compounds formed by highly reactive non-metals with highly reactive metals are generally ionic because of large differences in their electronegativities. On the other hand, compounds formed between non-metals themselves are largely covalent in character because of small differences in their electronegativities. Whenever there will be less difference in electronegativities, then they will form covalent bond. Okay, this is important thing. Compounds formed between the non-metals themselves are covalent in character because of a small difference in their electronegativities. The change of non-metallic to metallic character can be best illustrated by the nature of oxides they form. The non-metal oxides are acidic or neutral. It is again very important things. Question is asked. The non-metal oxides MO, just generally in general way, the non-metal oxides are acidic or neutral, whereas metal oxides are basic in nature. Always keep in mind, metal oxides always metal because they want to give the electron, lose the electron. That's why they have those metals who wants to lose the electron are called basic. Basic, and it will form basic oxide. Okay, and non-metal they want electron. That's why it is oxide. The non-metal oxides are acidic. Non-metal oxides are acidic and neutral. Okay, or neutral, whereas metal oxides are basic in nature. This is very important things I told you. The first member of P block differs from remaining members of their corresponding groups in two major respects. They differ. First is the size and all other properties which depend on size. Okay, two major respect I told you. The first is the size. First is the size and all other properties which depends on size. Thus, the lightest P block elements in the beginning, the lightest P block elements show the same kind of differences as the lightest S block elements. Similar it is there. The lightest P block elements show the same kind of differences as the lightest S block elements, lithium and beryllium. The second important difference, two respect I told you, now second you can see. The second important difference which applies only to the P block elements arises from the effect of d orbitals in the valence shell of heavier elements starting from the third period onward. Okay, D block will start vacant D block elements. Okay, applies only the P block elements is arises from the effect of d orbitals in the valence shell of heavier elements starting from the third period onward, and their lack of second period elements In second period element D block you can't find the D block, only third period onward. And in second no D block elements are there. That's why difference is there. Okay. Again you can see further. The second period elements of P groups starting from boron and restricted to a maximum covalency of 4 using 2s and 2p orbitals. In contrast, the third period elements of P group with the electronic configuration 3s square 3pn have the vacant d orbitals, vacant 3d orbitals lying between 3p and 4s. Okay, 3p and between the 3p and 4s, 3d will be there. 3d orbitals will be there between 3p and 4s levels of between 3p and 4s levels of energy. Okay, 3d orbitals will be there always between, because this will not fill completely. 3d and 4s will start. That's why it will lie between 3p and 4s levels of energy. Using these d orbitals, using this d orbitals, the third period elements can expand their covalence above 4. You have seen that generally outermost orbit, how many are there, or they will have oxidation state like that way. But here D block elements are there, that electron can give. That's why more than 4 is also possible. Okay, more than 4 oxidation state is also possible. Using these d orbitals, the third period elements can expand their covalence above 4. For example, while boron forms only BF4, aluminum gives AlF6 3-. Okay, boron forms only BF4 1-. Okay, aluminum gives AlF6 3- ion. Okay, the chemistry of the behavior the chemistry of the heavier elements in a number of means their variation I am talking about. The chemistry of the heavier elements in a number of other ways it vary. Okay, the presence of these d orbitals, influence the chemistry of heavier elements in a number of other ways due to d orbitals. Elements present in the d orbitals, that their chemical reaction properties, or you can tell chemistry of the heavier elements vary, means influence the chemistry of heavier elements in a number of ways. The combined effect of size and availability of d orbitals considerably influence the ability of these elements to form pi bonds. Okay, pi bond is not only due to p. The pi bond is not only due to p. It is also due to d orbitals. Keep in mind, the combined effect of size and availability of d orbitals considerably influence the ability of these elements to form pi bonds. The first number of a group differs from the heavier members in its ability to form pi multiple bond. Pi multiple bond to itself. As for example, you can see carbon-carbon double bond, carbon-carbon triple bond. Then here one bond is sigma bond and other bond is pi bond. Carbon-carbon double bond is there. Then one bond is sigma bond and other bond is due to pi bond. Other bond is pi bond. And similarly, carbon-carbon 3 bond. One bond is sigma bond and other two bond is pi bond. Okay. Then this like that way, nitrogen triple bond. Nitrogen N2 gas between the N and triple bond is there. Okay. Then here also same way, one sigma bond and other two pi bond. And to other second row elements, now we talked about the third. Now other and to other second row elements, example, that is the CO carbonyl group, COO, that is also pi bond is there. CN triple bond is there. C double bond N, cyanide isocyanide. C double bond, C triple bond, N double bond. Everywhere pi bond is there. Pi bond is there in all the things, and in all the things only p block making this pi bond, only p block elements are not responsible. D is also responsible. Okay, F is also responsible in higher periodic table. Down if you go third onward, then F will be also there. Okay. Then this type of pi bonding is not particularly strong. Okay, for the heavier p block elements. Pi bond is there, then pi bond already know is a weak bond because this is the lateral overlap, side-wise overlapping, not too much overlapping. Side-wise overlapping or lateral overlapping means weak overlapping. Hence a bond formed is weak. Okay. Then this type of pi bonding is not particularly strong. Okay, for the heavier p block elements. The heavier elements do form pi bonds. Okay, the heavier elements do form pi bonds, but this involves d orbitals. D orbitals means d pi p pi you can tell, d pi p pi or d pi d pi, both are possible. Okay, only pp is not, pp is there but only in the beginning. First element there they can make. pp is also there, d pi and p pi is also possible. p pi is there, d pi p pi is also there, and d pi is also possible. Three type. Okay, first you have seen pi bond, after that d pi p pi, and third d pi means p pi first, and second is d pi p pi, and third d pi. As the d orbitals are higher energy, of higher energy than the p orbitals, they contribute less to the overall stability of molecules than does the pi, because d belongs to the higher energy. Then higher energy means bond will be weak. Higher energy means always instability. Okay, as the orbitals are of higher, d orbitals are of higher energy than the p orbitals, they contribute less to the overall stability of molecules than does pi bonding of the second row elements. Okay, However, the coordination number in a species of heavier elements may be higher than for the first element in the same oxidation state. Here, coordination number means you should understand not generally always coordination number exists in the complex compound. In the complex compound, central metal ion will be there, and with this central metal ion, like maybe chromium, maybe nickel, okay, then around this how many, or you can say from the central metal ion, how many, you can say this groups are attached, that is called ligands. Number of groups attached to the central metal ion may be OH, maybe chloride, maybe bromide, maybe iodide, maybe H2O. these are called ligands, and they will attach directly to the central metal ion. Then number of groups attached to the central metal ion, that is called ligand. Okay. Then the coordination number in a species of higher elements may be higher than for the first element in the same oxidation state. Oxidation state may be the same, but ligands may vary. For example, +5 oxidation state, both N and P form oxoanion. See here. +5 oxidation state for both N and P, nitrogen and phosphorus. Nitrogen and phosphorus belong to the same, but they vary oxidation state. +5 oxidation state. +5 oxidation state, both N and P form oxoanion. Okay. Nitrate ion, 3 coordination. Nitrate ion, NO3 1 minus, 3 coordination with pi bond involving this pi bond involving one nitrogen, p orbitals, and phosphate, 4 coordination number. See, in N you have seen +5, then in N 3 coordination, NO3 1 minus is there, then 3 coordination with pi bond involving one nitrogen, p orbitals. Nitrogen has p orbitals, 3 p orbitals, then one electron. Okay, 3 coordination with pi bond involving one nitrogen p orbital. And in phosphate PO4 3 minus, 4 coordination involving S, P and D orbitals. Here this is the important. Phosphate, you can see orbitals, how many orbitals are taking part. Then 4 coordination, PO4 is there, 4 oxygens are there. Then 4 coordination involving S, P and D orbitals. Okay. Then here you can see this 4 coordination number. How did it come? S, P and D orbitals contributing to the pi bond. But in NO3 3 coordination number with pi bond involving one nitrogen p orbitals. Okay. Now I am going to discuss group 13 elements. Group 13 elements, that is the boron family. Okay, because in this P group 6, in P block element 6 groups are there. In P block element 6 groups are there. Then now I am going to discuss this thing 13, group 13, 14, 15, 16, 17, 18 are there. And then now I am starting with 13, group 13 elements. Okay, that is the boron family. Boron is very, very important. Okay. This group elements show a wide variation in properties. Boron is a typical non-metal. Boron is a typical non-metal. Aluminium is a metal. Okay, aluminium is a metal, don't forget. But shows many chemical similarities with boron. Despite aluminium is a metal, it shows many chemical similarities to boron. Okay, boron. And gallium, indium and thallium are most exclusively metallic in character. These three other members are gallium, indium and thallium. Boron, aluminium. Okay, boron, aluminium, these things, with this carbon I am talking, not carbon, with boron group, boron is there. Okay, boron, aluminium, after that gallium is there, indium is there, thallium is there. These are exclusively metallic in character. Boron is a fairly rare element. It is found in very less quantity. Boron is a fairly less element, mainly occur as a orthoboric acid, H3BO3, and other form is borax, Na2B4O7, 10H2O. Borax is very, very important compound of boron. Borax, Na2B4O7, 10H2O. And kernite, 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 again same things, Na2B4O7, only water molecules is different. Now it is 4H2O. Kernite, again same, Na2B4O7, only difference is 4H2O, and in borax it is 10H2O. In India, borax occurs in Puga Valley, means Ladakh, okay, and Sambar Lake, Rajasthan. The abundance of boron in earth crust is less than 0.0001% by mass, very less, 0.0001%, less than that. There are two isotopic forms of boron, B10, mass number 10 and mass number 11. They are different because of number of neutron is different. The B10 is found only 19%, and B11, that is found 81%, means B11, mass number 11. Then both are differing, both are isomer, B10, B11, differing by number of electron is less in B10 and 11 it is one more. Okay, and aluminum is the most abundant metal. Actually, this boron family I am talking about. Then boron I told you. Now come to the aluminum. Aluminum is the most abundant metal and the third most abundant element in the earth crust. It is found in more quantity, 8.3%. It is the third most abundant element in the earth crust, 8.3% by mass, after oxygen and silicon. First is oxygen, it is found 45.5%, and silicon is the second, 27.7%, and aluminum is third, 8.3%. Bauxite means Al2O3 2H2O, bauxite, and cryolite, Cryolite, cryolite. Cryolite, Na3Alf6. Aluminum is Al2O3 2H2O. Okay, bauxite. It is a very important role of this ores of important ores of bauxite. Okay, aluminum. Bauxite is the important ore of aluminum. Very important ore of aluminum. Cryolite is also important ore, you can say ores of aluminum. Na3Alf6 cryolite. These are the important, you can say, these things. Aluminum is found in the form of bauxite and cryolite. Okay. These are the actually also contain minerals, are the important minerals of aluminum. In India, it is found as mica, M-I-C-A, mica, in Madhya Pradesh, Karnataka, Orissa, and Jammu. Okay. And what about the gallium, indium, and thallium? Then gallium, indium, and thallium are less abundant elements in nature. They are found in less quantities. Okay. The atomic, physical, and chemical properties of these elements I will discuss in the next class. Okay. Thank you.